The best way to understand isochron plots is to look at a real example. This is a sample of Gabbro, an igneous rock. The question is, how old is it? You can see that it is made of crystals of different materials. The three main minerals present are pyroxene, the dark mineral, feldspar, the light-coloured mineral, and a third green-coloured mineral called olivine. As well as these three minerals, there are small amounts of impurities that get included as the crystals form. We are looking for an isotope in these impurities that is radioactive and which we can use as our clock. Firstly, I need to remind you about radioactivity. Radioactive elements have nuclei that are unstable. Small bits are shot out of the nucleus to help it become more stable. When this happens, the identity of the radioactive atom changes and it becomes a different element. This equation that looks complicated is a maths shorthand for a simple physical rule that radioactivity follows. The first bit, we say d by dt, means the rate of change with time, and n is the number of atoms of the radioactive element. So the equation says the rate at which radioactive element is changing to the new element depends on how many atoms there are. The more atoms, the faster they disappear. We will need this fact later on. The character lambda in the equation is called the decay constant. Some radioactive elements decay quickly and some much more slowly. Lambda is a number that controls that speed. For our impurity, we wanted to have a decay constant that is very, very small, so it decays very, very slowly. All elements that are radioactive were formed before the solar system formed 4.5 billion years ago. Those that have big values of lambda will have disappeared long ago. The element we are going to use is samarium, number 62 in the periodic table. Samarium is present as an impurity in all three minerals in the Gabbro. Samarium has 7 isotopes. Just a reminder, isotopes have the same number of protons, plus charges in their nuclei, but different numbers of neutrons, neutral particles. The figure 62 is the atomic number. This controls the chemical behaviour of the atoms. The top number is the mass number, adding protons and neutrons together, and this controls the physical behaviour of the atoms, affecting things like density. We will need these facts later on. Samarium has 7 natural isotopes, 5 stable and 2 radioactive. We're going to use Samarium-147. It decays by emitting an alpha particle and turns into Neodymium-143, which is a stable isotope. Its lambda value is 6.5 times 10 to the minus 12, so it has a very, very slow decay. Let us think about how the Gabbro is formed. The scene is inside a magma chamber that is beginning to cool down. The slower it cools, the more time the atoms in the crystals have to bond together and the bigger the crystals get. Of the 3 minerals, the first to crystallise is olivine at a temperature about 1300 degrees Celsius. The pyroxene then crystallises at about 1100 degrees, and lastly the feldspar crystals form. The samarium is included in the crystals of olivine, so the concentration of samarium atoms left in the molten magma is less. As the pyroxene crystallises, it too takes some samarium out of the melt. This means that there is still less to enter the feldspar crystals. So, to recap, olivine has the most, pyroxene has less, and feldspar has least samarium included in it. To measure the amount of the isotopes present in the crystals, we can vaporise the crystals using a targeted laser beam and analyse the data with a mass spectrometer. At this point, we have data about all the isotopes of both samarium and neodymium. You have to realise that when the rock form, both samarium and neodymium are included in the minerals as impurities. The problem now is, how do we use the data to find the age of the rock? Look at the axes of this graph. Instead of just plotting the Samarium-147 along the horizontal axis and the neodymium up the vertical axis, we are plotting ratios. The denominator in each case is the amount of neodymium-144. The geological scale on the right shows that we are at 350 million years ago, when the rock was new. There is a horizontal dotted line, and on it are the three minerals. Isotopes of neodymium behave chemically the same as each other. Whatever ratio of the two amounts of isotopes of neodymium-143 and 144 were in the melted magma, they would have appeared as impurities in the crystals in the same proportion. This is chemical behaviour. So the neodymium ratios in each mineral sample will be the same when the rock is new. Why are the three minerals at different points along the dotted line? We said that most samarium goes into the olivine, then the pyroxene, and last the feldspar, so this spreads them out horizontally. We are going to animate this graph in a minute to simulate the passage of time to the present day. But first, let us see if we can predict what will happen. On the horizontal axis, samarium atoms will disappear as it decays, so we will move left. On the vertical axis, we will gain atoms of neodymium-143, so we will move upwards. Do we have any other facts to help us? Well, the rule of radioactivity says that if we have more atoms, they will disappear faster. Olivine has the most samarium atoms, so olivine should go quickest, then pyroxene and feldspar slowest. Let us animate the graph and see if we are correct. It is now present day. We have a 350 million year old sample of Gabbro, and this is how the plot looks. I have added a straight line which aligns with each sample. This is a line of equal time, or an isochron. The greater the gradient of the line, the older the sample is. The exact age is calculated from the gradient using this equation. M is the gradient of the graph, and lambda is the decay constant as before. The left isochron plot is from the Juvenus meteorite that fell in France in 1826. The plot shows an age of 4.56 billion years. The right-hand plot is from a sample of moon rock and shows that it has a similar age. The composition of the chemicals in a magma chamber will not be homogeneous, so taking samples of whole rock from different places in an outcrop will give an isochron plot, although The positions on the plot are likely to be closer together than when using individual minerals, and therefore the plot will be less accurate. The Samarium-Neodymium Isochron plot works well for rocks like Gabbro, but these isotopes do not absorb well into the minerals of granite, a rock that is made up of quartz, feldspar, mica and amphibole. There are other isotopes like rubidium with very slow decay rates that will absorb into the crystals of granite and which can be used to produce similar isochron plots. Samarium and rubidium can cover rocks of most ages, except for very recent ones where the gradient of the isochron is small.